This video is a step-by-step solution for the example entitled Cooling a Gas in a Piston Cylinder. In this example, you will learn about evaluating the heat transfer for a gas in a piston cylinder assembly undergoing a polytropic expansion between given initial and final states. Let's look at the problem statement. 4/10 of a kilogram of a certain gas is contained within a piston cylinder assembly. The gas undergoes a process for which the pressure-volume relationship is PV to the 1.5 is equal to constant. The initial pressure is 3 bar, the initial volume is 0.1 cubic meter, and the final volume is 0.2 cubic meter. The change in specific internal energy of the gas in the process is U2 minus U1 equal minus 55 kilojoules per kilogram. There are no significant changes in kinetic or potential energy, and we have to determine the net heat transfer for the process in kilojoules. First, let's do a critical read of the problem statement, highlighting in red the important information given, and in green the information requested. 4/10 of a kilogram of a certain gas is contained within a piston cylinder assembly. The gas undergoes a process for which the pressure-volume relationship is PV to the 1.5 equal to a constant. The initial pressure is 3 bar. The initial volume is 0.1 cubic meter, and the final volume is 0.2 cubic meter. The change in specific internal energy of the gas for the process is U2 minus U1 equal minus 55 kilojoules per kilogram. There are no significant changes in kinetic or potential energy. And we have to determine the net heat transfer for the process in kilojoules. Let's start to develop the solution. The first thing to do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in a critical read of the problem statement in a more compact bulleted list format. A gas within a piston cylinder assembly undergoes an expansion process for which the pressure-volume relation and the change in specific internal energy are specified. The next thing to do is to summarize what we have to find. This is again the same information we highlighted in green in a critical read of the problem statement, presented here in a bulleted list. Determine the net heat transfer for the process. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few key pieces of information to help guide our solution. The first thing to note is there is no mass entering or leaving the piston cylinder. This immediately suggests that a closed system approach is appropriate. Having recognized this important fact, let's select a system boundary. Remember that a closed system does not allow any mass in and out through its boundary. Here, it is selected to enclose the gas and follow the physical boundary of the piston cylinder assembly as delineated on the schematic with the red dashed line. It ties in the information provided to the information requested, namely the pressure-volume relationship, a polytropic process with n is equal to 1.5, and the change in internal energy for the system. The next step is to develop an appropriate thermodynamic diagram to represent the process. In this case, the PV diagram is shown here. The process follows a polytropic relationship PV to the 1.5 is equal to constant. Also note that the area under the curve in the PV diagram can be interpreted as the value of the work, as shown here with the shaded area. The next step is to develop an engineering model. In other words, listing a set of simplifying assumptions which will allow us to perform the analysis of the problem. The gas is a closed system. The process is described by PV to the 1.5 is equal to constant. And there is no change in kinetic or potential energy for the system. Having completed all the required initial step, let's develop the analysis. The energy balance for the closed system takes the following form. Delta kinetic energy plus delta potential energy plus delta internal energy is equal to Q minus W, where the kinetic and potential energy terms drop out by assumption. Then, expressing delta U in terms of the specific internal energy, the energy balance becomes M times U2 minus U1 is equal to Q minus W, where M is the system mass. Solving for Q, we obtain the following expression. Q is equal to M times U2 minus U1 plus W. The value of the work for this process is determined by referring to the solution of part A of the example entitled Evaluating Expansion Work. In that example, we obtain W is equal to plus 17.6 kilojoules. The change in internal energy is obtained by using the given data for the specific internal energy change through the process and the given value of the mass. Substituting the values, we obtain the following. M times U2 minus U1 is equal to minus 22 kilojoules. Finally, substituting this value and the value of the work obtained in the corresponding example into the expression for the heat transfer, we obtain the following. Q is equal to minus 22 plus 17.6 kilojoules, which is equal to Q is equal to minus 4.4 kilojoules, which is the answer we were seeking for the heat transfer during the process under the conditions specified. In closing, I would like to make a few comments. The given relationship between pressure and volume allows the process to be represented by the path shown on the PV diagram. As mentioned earlier, the area under the curve represents the work. Since work, as well as heat transfer, are not property, their values depend on the details of the process, that is, the shape of the path, here characterized by the specific exponent of the polytropic process, n equal 1.5. Heat and work are not properties and cannot be determined from the end states only. The minus sign for the value of the heat transfer Q means that the net amount of energy has been transferred from the system to its surrounding by heat transfer. In summary, in this example, we have learned about evaluating the heat transfer for a gas in a piston cylinder assembly undergoing a polytropic expansion between given initial and final states. This concludes the step-by-step solution of the example entitled Cooling a Gas in a Piston Cylinder.